Okay, guys. So now we're in lecture 8. What I'm going to try this lecture, I think we'll have some time at the end. And so I'll give you guys a quiz question on something. Just want some extra time. So I think I'll give you guys a quiz on this because we went over this a couple of times. And we went over like a little bit in depth last time, but okay, well, let me ask you, does anyone have any questions about how to plot in these steaming log plots and also the magnitude and phase? Any questions about that?
Can you go over it?
Huh?
Can you go over it?
Oh, yeah, sure. Since you might be a quiz on it. Okay, so what typically happens is that you're given a transfer function, and it's steady state. So that's why this is just j omega and not s. S is typically for like transient analysis. But with steady state, then it's just j omega, and it may not be in this form, right? But what you need to do is, if you get it into this form right here, then it makes it a little easier to work it out by hand. Okay. So so typically what you want to do is you want to group your numerators factors and your denominator factors like this, where they have the form of the real part is just 1, and the imaginary part is just omega over some value. And that value, once omega gets that value, that's going to be a cutoff. And the denominator, it happened like this too. And each part that you factored, it came out, and it all got grouped together in this piece right here. Okay, so you have four quantities here. You have this quantity right here, 2 on top and 2 on the bottom. Okay, so now once you take the magnitude and you put it in terms of decibels, this fraction right here works out to be like this, where each of these quantities are each of these. The numerators are added together and the denominators are subtracted. And they're in the form of 20 log of whatever the magnitude is for that quantity. So in this case, since this real is 1.5 e to negative 3, the magnitude here is the magnitude of this piece right here. And this is minus because it's on the denominator, so is that minus on the denominator. But you just take these pieces right here and they go in there. And so that's what the equation looks like. And this is what you're plotting, magnitude as a function of frequency. And so if you put that into a computer, it would just generate this blue curve, but the vertices would be smoothed out. It will generate this blue curve right here. But to do it by hand, you want to notice a few things about this. And what you notice is that whenever omega equals the denominator, then that becomes 1. And then you have the magnitude of 1 plus j1, which is square root of 2. Okay, and that's for all of them. When that omega happens to equal 100, you have the magnitude of square root of 2. And then when that omega equals 500, you have the square root of 2 as well. Okay, but so 20 log square root of 2 is going to be 3 decibels, but it's going to be minus 3 decibels. So you have minus 3 decibels here. This becomes minus 3 decibels at that cutoff. At this cutoff, this becomes plus 3 decibels. Okay, and that's where you put the cutoffs at. So you have a cutoff right here at 10, and that's going to be 3 decibels right here, which is like a little bit above that. But just put your asymptotic values here. For this one right here, you're going to have -3 decibels where it's going to cross this piece right here. And then for this one alone, there's going to be -3 decibels at that cutoff right there. Okay? So after you've plotted each one individually, so this piece right here is this one, number 1. If you just, if that was all you're plotting, that's all you would get. If all you're plotting is this, you'll get this piece, and it turns right here, and it goes up like that, asymptotes to that, and you go right there. But of course, it smooths out and crosses the 3 decibel point. And if you're plotting those two, you'll plot this 3 curve and that red 4 curve. And then after you finish plotting each of your terms, then you just add them all together to generate this blue curve right here. Okay. So any questions about the magnitude plot? You guys are okay with that? Okay. So let's turn to the phase plot. Okay. What's different about the phase, between the phase and the magnitude, is that instead of you being at the plus or minus 3 decibels at the turning point right here, you're at the 45-degree part, or negative 45 degrees here and here. Okay. So that's one thing you have to keep in mind, and that's for each one individually. Another thing you want to notice is that once you go up a decade from wherever your 45 degrees point is, you go up here and then it flatlines. If you go down, a decade and that along that slope, it flatlines like that. I mean, we didn't continue this, but if this was that's 500, 100, 10, that was 1, and then 0.1. 0.01 on, this would be flatlined right there. Okay. Same with these. They're at negative 45 degrees, and they're at negative 45 degrees because they're on the denominator. These two right here. So negative, negative. Right here. Then they go up a decade, flat line. Go down a decade, flat line like that. Same with 4. So at 500. Go to the decade, flat lines, and decade and flat lines like that. Yeah, so all you gotta do is just be careful like where your decades are, because for example, this one is at 500, right? So that's 100, 200, 300, 400, 500 right here. And when it goes up, it has to be right here, that's gonna be 50, right? Because that's 10, 20, 30, 40, 50. And over here, that's going to be 5,000, because but that's 500. Okay, that should be 1,000 right there, not 100. Okay, so that should be 1,000, then 2,000, 3,000, 4,000, 5,000. So that's your decade. And then once you have all of them, all plotted out. And I forgot this one. This one's going to be 0. It's real. So that part right there is, totally vague. So 0. But once you have all of them plotted out, you just add them all together graphically, like that. This one's a little more complex, right? But the same thing applies. Okay. So any questions about the phase? It's good? Okay. Great. All right. Okay, so if someone gave you this blue plot, would you be able to work backwards? You guys feel like you could work backwards with that?
I don't think so.
Yeah.
Yeah.
Okay.
Probably not.
I'm trying to think of a quiz question.
Magnitudes,
I mean, because here's what I'm thinking. If you were given like a blue curve like that, and then you would have to think, what kind of lines, they're like, first they're straight, and then either they go up at 20 decibels per decade or down 20 decibels per decade. How many, like, what kind of ways would I be able to generate that using just those kind of things? Can you guys see it now? Can anyone not see that? Okay, good. That would be the quiz question. Okay. I mean, because you see how this was generated from these. So this other stuff is working backwards, and these lines, wherever they, they start over a decade over, it's the same point, and they just keep on going forever like that, and then it's flat line like that before it gets there, right? And so you just have to think about graphically how to add them together, or to break them out from this.
So given one of the lines, would all of the other ones always look the same relative to the line that you have?
Wait, say that again. I didn't-
So the three other colored lines, depending on which one you have to work with, do they always follow accordingly based on that graph? Like, given the scale of the...
Oh yeah. Like for these right here, they all, their flatline parts is always at zero magnitude.
Mm-hmm.
How this thing raises up or lowers is from that first piece.
Mm-hmm.
That's it. Like, if this was not there, if we didn't have this whole blue curve would be up there,
Okay.
and this line right here would be right there.
And
So-
all the other ones that move?
Yeah.
With
So,
it-
yeah. So think of that as like a DC offset,
Mhm.
but everything else, the same shape would arise up. Yeah.
So when you say work backwards, do you mean finding the transfer function or just the other lines on the graph?
I would just have you get the other lines on the graph. I mean, you could even generate this, because all of these are from that, right? Now this one right here, you need a calculator for that. So depending on where this ended up, you could generate that. So I mean, it's possible, but going from here to here, that's also another step that you can see, because you're saying, because you can see, oh, these are negative, so both of these are going to be in the denominator, right? And both of those are in the numerator, so it's conceivable. But I think just first I'd have you guys just do the lines just to get started. Okay. So anyway, moving right along. Okay, so last time we met, we talked about looking at these amplifiers, and then we applied Blackman's theorem right here, and we took the amplifier to look like this, and of course different kind of configurations were given, and we abstracted those into like a series or a shunt between the ports, the input ports and output ports of the amplifier. And we also looked at the amplitude, the loop gain, the short circuit loop gain, the open circuit loop gain, and the Rn if you turn up all the internal sources, and also the overall resistance, looking from maybe the input port or the output port. Okay, so now one thing I was just thinking about, and I got this from the web, is the difference between positive and negative feedback, right? So, so if you look at this figure right here, you can clearly see that, for positive feedback, it looks like the feedback loop just goes right into the non-inverting node. And for negative feedback, it goes into the inverting node. But as you'll see today, our circuits aren't as simple, where all of our circuits that we will look at today they're all negative feedback, even though it'll feed back into maybe the non-inverting node. I asked one of the other professors who teaches this on a regular basis to clarify that. So I'm waiting to hear back. But basically, this sort of holds true, right? For the parameter, you have your phase shift, you have your input-output voltage with noise, your feedback signal, the gain, stability, and applications for use. This column right here is for positive feedback, right? So your overall shift is going to be 0 or 360. Okay, which is basically the same thing. Now, for positive, the input-output voltage it increases due to feedback. Okay, the feedback signal and input signal, they're in phase. The gain increases due to that positive feedback, but the stability is very poor because of that. So you're like, you're really worried about the whole thing just blowing up in terms of your output signal. But it's typically used for oscillators. For negative feedback, you're 180 degrees out of phase, right? Which is typically just a negative sign, right? I mean, it's the opposite sign of whatever's coming in. It decreases due to feedback. Of course, your feedback signal, input signal, they're out of phase, 180 degrees. The gain is decreased. It has much better stability than this, because it's negative feedback. And it's typically used for amplifiers, which is why we're looking at it today. Okay, so here are the concepts. So here's where we left off at the series, but we went over it kind of fast, so we'll go over it again. And then we'll look at the shunt series. And then we'll look at finding the loop gain using successive voltage and current injection, because sometimes you have to do it this way. We'll explain why. And also look at distortion reduction due to feedback. And that's negative feedback, where you can reduce your distortion. Okay, so series. So we left off with this right here. Here, this was a system, right? And so the book says, the series input, the reason that this is helpful is because this to accurately measure an input voltage. So you need a high input resistance, and so that's why that's called in series. And for the series output, to produce a good current source, right, you need a high R out for that. Okay, so depending on what your application is, you'll determine what kind of shunt, what type of amplifier that has a shunt or series in the beginning, in the front, or shunt or series in the back, depending on what you're trying to do. Okay, so for this transconductance type of gain right here, it's going to be your output, which is the current, over your input, which is your voltage. And you can look at it in terms of an ideal amplifier multiplied by this correction factor, which is T over 1 T. And T is your loop gain. Okay. Now the ideal, if you worked it out, the ideal would be negative 1 over R. And so, you would, I guess what you would do, this is voltage coming in, it's copied to over here, right? So you know what this voltage is, and then you can generate what this current is, and that's the current coming out right there. So if you look at the output over the input, you would get this right here, this negative 1 over R. Okay, and also, I guess you can see it's negative because if that was 0 volts, reference ground, and that is a high voltage, this would be a high voltage. So you would think current is going in this direction, but no current is going that direction, right? So this is a positive sense for current. So if you calculated a positive current, then you would know it's going this direction, but it's going to be negative, so the actual current is going down this path right here. That amplifier. Okay, so to do the analysis, we take this idealistic type of structure and we pull out the RID to like really make that more explicit, and also the amplification part, the voltage control voltage source, and also the output resistor. That's in there. That's in there too. Okay. And this part that's shaded right here, this is beta. This is our feedback. And here's like, the feedback is going through like this. So this is the feedback part, and that's part A. So remember our feedback system. It went through. What do we have here? We had something like this. Went through A, came out, and then it went through some beta, and that came through here. And this is plus, that's minus. And here's our input. Right? So that pink part right here is this. This part up here is this part right here. And so it's negative feedback. Okay, so it's going to be stable. Okay, so all right, so first what you want to do is look at loop gain for this right here. And so the loop, for the loop gain, you want to disable VI for this loop gain calculation. So I've taken the voltage source and turned it into short circuit. Okay, if this was a current source, it would just be open to turn that off. Okay, so for this loop coming back, you want to assume that this VID has some kind of input of Xn, or you can choose 1 volt for the voltage controlled voltage source right here. And then you calculate the value returned over here. Okay, so this part right here came from voltage division, and it's beginning at node Z and going around counterclockwise. So right here, and going around counterclockwise direction. And then this right here is loop out over the loop input. And that's basically, you're putting Xi in as the input, and this right here is right there. So those two cancel out, so you just get this right here. Okay. All right, and for the input resistance, what you want to do is look at your RND right here. You also want to look at what happens with your loop gain when you have an open circuit right here, and also when you have a short circuit right here. Okay, so when you have a short circuit, which means this is just going through like this at the port you're looking into, as you can see, that's just what we had last time for this short circuit. Same thing, right? So that's just what we've already calculated. If you have an open circuit right here, if it's open, there's no path there, so the feedback loop is 0. So T open circuit 0. So you just plug it into this. This part right here is what you get when you turn off all internal sources, meaning that you have to turn this piece off right here, because remember that was the voltage controlled voltage source, and so you just make your A0 B0. Okay, and then you have a short circuit right there. All your sources turn it off, and then you calculate what that is. Now, typically, if you have an active type of circuit, and I'm talking about in general, like if you're not using Blackman's formula, if you have some controlled sources in there, you typically don't want to turn them off. I mean, let me put it this way. All your dependent sources, all of your independent sources are turned off. Your current your voltage sources become short circuits, but your controlled circuits, your controlled sources, you leave them alone, okay? And then you apply an external voltage or an external current source, which may then activate the voltage controlled voltage source or the current controlled whatever you have in there, and then that's how you determine the resistance of that. Okay, but in this case, you turn them off. So that's one thing you just want to pay attention to. So that part goes right there, and then 2 parts go right there, and then that's where you get your Rn. So that's Rn. For R out, same thing on the out. Put over here. Oh wait, that should say out. So I'll fix that. So for the short circuit, if you close that, it's just like last time. The open circuit, it's 0. Again, you want to turn this off when you're trying to calculate that. Then you plug those values in, and this is what you get here. Okay, so now for the shunt series. So here's a new one. So is this circuit right here, and again, same kind of situation. This is this part right here is the same. The only difference is that between this one and the last one is that you have I out, but you have I in instead of B in. Okay. For the ideal gain, this is what you'd get for ideal gain. Okay. So to do some abstraction into the nonlinear, the non-ideal regime, you want to break out the resistance right here, and also the voltage control voltage source here. And then, so for your loop gain right here, yeah, okay. Yeah, so for your loop gain, a little more complicated, but one thing you want to do is do your voltage division starting at Y for this VID right there. So you start at Y, and you go around this way right here to where you start to where this part is. So this is your voltage across your beta here, right? And so your resistance is this RID right here, which is what you're measuring over. And then down here, the total is RID plus this R2. Okay, and we're not really including R1 because that's this is your voltage that you're starting from right here, from ground. Okay, it doesn't matter how it got there. That's your voltage that you're starting from. That's where this equation is. Okay, so for this equation right here, for this piece right there, to determine that, you can do voltage division starting at Z, right here. And then what you want to do is go around this way. Right? So you're starting right here as your reference, and you're going around this way. And what you're doing, you're passing through, this time you're passing through R1, but that's in parallel with R2 and RID in series. So R2 and RID are in series right here, going to ground. And it's parallel with this one going to ground because they're starting off at the same node here, and they're both ending up on this ground node right here. So electrically, they are in parallel. So this is in parallel with these two guys in series. Okay, but since you're going around this direction right here, on the bottom here, you have the entire route, which is this piece right here, plus you have additional R0, and you come back around to your main source. Okay, and that's right here. Now I've already included, your test voltage for your input. So that VID, I just put XIN right there. Okay. then what you do, you look at your loop gain, and that's the ratio of your output right here over your input, which is XIN right here. And it's negative because it's negative feedback. Okay, so the only thing that happens is that this little piece right here goes away, and you just get this. Okay. Wait. Let me make a correction. This piece right here was plugged into here. Okay. So here's your VID. That's why we have this extra term here. That extra piece back here. Okay. All right. So for the input resistance, for this piece right here, if it's an open circuit, then this is the same thing that we got from our gain calculation before. If it's shorted like that, then that's ground, and so that's all ground right there, and it's all zero because no signal will develop across this RD. Because if that's ground, that's going to be ground. You're not going to get a signal out of that. Okay. For this right here, for this RD in, what you're going to do is turn this off, right? And then you calculate what your value is for this. And then you take those three things, plug them in here, and that's what you get. Okay, that's for the input. For, I'm still calling this in, this out. For the output, you want to do the same thing here. If it's shorted, you get the same thing that you had before for your loop gain. If it's open circuited, it's zero. Okay, and your R out is from turning off your sources. That's what you get. And also, that's turning off this means it's going to be open circuited because it was a current source. And then plugging those values in here, you get this. Okay, so now let's move on to loop gain calculation, like another type of method. But before we go on, are there any questions about these last two, the shunt series and the one before was I think it was series. You guys okay with that? So we went over all four possibilities, okay, for those types of things. All types of combinations of that. Okay, so now for so these loop gains, they're often used for stability, to maintain correct operating points, or to prevent input noise from saturating the amplifier. So when the feedback loop is necessary for proper operation, opening up the feedback loop to measure loop gain, like experimentally, may not be a viable option. So for such cases, the loop gain may be measured by the method of successive voltage and current injection. Okay, so we're going to look at that now. And this also happens too, like if you have a very high gain right here on your loop, if you try to open that up and measure that, that actually affects your entire amplifier, so you're not going to get a valid result by doing it that way. But here's one way you do it. So in this method, what you do is first you choose an arbitrary point in the feedback, and then at that point, so here's like point P right here. Okay, I should have drawn a P here. So this is P, and that's P right there. Okay, so first what you do, you inject a voltage Vx to get your loop gain for your voltage injection, and then you inject a current to get your loop gain for your current injection. So here's the voltage that you're injecting. You did that experimentally, some kind of way. And then for your current, you actually put your probe there, or some kind of current source. You actually put in current right there. Okay. And then what you do, you measure those two things. Okay. So in this case, for the voltage injection, this is a little weird here, but here we're looking at it and we see what the resistances are. But basically, we're going to think in terms of this RA and RB. So, from the perspective of looking at it on this side right here, coming out of here, what this sees is an RA in this, in this direction, looking that direction, and then over here from this node, you see like an RB just looking in that direction, effectively, whatever that is. Okay, so for your V1, well, first of all, you're going to assume your beta is RA over RA plus RB. Okay, and this is your feedback. This type of beta happens a lot. You guys, can you guys recognize where this comes from? That term here? Is it here? Huh? It's like voltage division. You guys see that? You guys recognize it? It's like the voltage that you're looking over divided by the total voltage you're going through. If they just take the voltage out in like this, like some ratio, because remember this is gain, output over input of a voltage. So if you separate it back out, it would be V out, and you take that V in, you put it on this side, and it's just voltage division. So that's why beta often looks like this. It's not always, but a lot of times it does. Okay, but if you like plug that in here, and if you get, if you did the math, you would get this expression right here for V1 in terms of this Vx. Now, this is a little tricky. This Vx, okay, so let me ask you this question. Is the voltage here Vx? Yes, no, maybe? Okay, so we know that voltage is V1. Is Vx equal to V1? Why is Vx not equal to V1? Huh? Yeah, now if this was grounded, right? If that was grounded, it would be equal. But that's V2. V2 is like, with respect to ground, that voltage right here is V2, right? So if I go through here, the voltage right here is going to be V2 plus Vx. You guys see that? Right there? So, I mean, you could say V1 equals V2 plus Vx, but this thing here is a change in voltage of Vx going that direction. Okay. Okay, it's right here. All right, so yeah, so this is V2. Okay, yeah, so like what we just said was V1 equals V2 plus Vx. I put that on that side. But you could like take that V1, plug it in here, and reduce it to this kind of form. And then your TV is going to be negative feedback of V2 over V1, right here, V2, V1. And then if you make the connection that wherever you see A, B, or A beta, you replace it with T, because we know that from a few lectures ago that's what we define loopback gain to be. Then you can pull out this A beta and put a T there, is what you have after that. So that's this first part. On this part right here, you do you do your currents, I1 right here and I2, figure out what those things are. Then you take your ratio of those two things, and you come out with this right here. And then once you have that, then you can take these two equations right here, and you can substitute them where you see the RA over RB, bring them together, then you'll end up with something like this. Okay? And this is really nice because this is what you're measuring with your probe in the lab, right? You're measuring the voltages V1 and V2, and you're measuring the currents I1 and I2, right? And that's what the ratios of these are. So you can determine what T is for the entire loop going around just from that. Okay. You guys see that? Okay, and for the last thing right here, this is something on distortion reduction through the feedback. And here's why distortion gets reduced if you have like negative feedback. So let's say we have a signal going through here, and we have this distortion that's added to it right here. So this distortion, so this piece right here is going to be amplified going through, but plus you're adding some distortion to the whole thing. So if you think about it, it's like this. So maybe VI was like, I don't know, A cosine omega t plus no phase coming in, right? So let's just say it's that. And then for the output, you have, this is going to be magnified, amplified somewhat. This is going to be the fundamental, but you may be off by some phase, say. But then you're going to have some distortion terms. You're going to have another term here. Let's call this 1 here. We'll put a 1 here for placeholder. You're going to have the second harmonic right here. Right? And then you're going to have, the third harmonic, and on like that. So this stuff right here, that's your V, the error term right there. Okay? That's what those are there. So your V out right here is this signal coming in plus your error. Your VID right here is your VI minus beta V out. So here's your V out. It goes through your beta right here. It goes back in, but it's negative feedback. Okay? So that's what that is. And here's our beta, which looks very familiar again. Okay? And then so with your V out, it looks like this. It looks like this factor times your V coming in plus this factor times that error, that your disturbance, your higher order harmonics. Now the thing is A could be, okay, so this term is going to be larger than this term by a factor of A, clearly, right? But this right here in particular, the denominator is always going to be larger than 1, right? Well, typically. So this is why your error terms are attenuated when you take it through a negative feedback amplifier. If it was positive feedback, this is going to blow up that term right there. Okay. Okay, we have 4 minutes for a quiz. Okay, so take out a sheet of paper. If you don't have a sheet of paper, borrow it from your neighbor. And I'll draw loading plot for you guys.
Your favorite jam make a mute for something else? Times 2 pi out. Oh yeah, that's just by definition jam make a mute.
That's what I was looking for.
Oh, did you not know that?
That's awesome. That's not funny. So this is open again.
It is something like that. Call it points. Oh, this right here?
Yeah.
Oh, this is like this M0. That's the maximum value right here. That's the same thing as well. It's just a value, like this value right here. Just so it's all symbolic. Yeah. Oh, and on your when you turn your paper in, oh yeah, you just put your name on it. That's fine. I was gonna say put your ID, but.
I'm sorry, but are you looking for the transfer function or?
Oh no, just these parts right here. Like, figure out what these lines look like. Those breakout lines right here.
Okay, so
That's
you
it.
only want like equation.
Yeah, no equation. Yeah. I mean, just because it's new. I mean, I've never done it before, so so it's like just a new thing to try out. So. But it does test your understanding of what's going on, I think. Let me put like an offset in there too. Sorry. Yeah, I kept on going. Call this like MPC offset. Okay, so if you guys are all done, just turn in your papers up front.